Thank you. So my name is Hibaaq Mohamud, and I work at the National Physical Laboratory. And this talk is quite a nice follow-on from the talk that Maximilian gave on technetium separation. And I'd just like to take the opportunity to kind of give an overview of the work done in the past couple of years to look at the separation methods for technetium in a range of applications, with a particular focus on how Trustchem's products have really helped with the work that we're doing to look at the production of technetium tracers. Fine. So for today's talk will be a bit of an overview on the motivation, which was covered really well earlier on by Maximilian, but I'll kind of just sort of kind of repeat some of the main sort of key challenges associated with measurement of technetium and why offline chemical separation or online chemical separation is required to measure technetium. And then I'll go through some of the schemes developed over the past couple of years by the group. So just a quick kind of plug, I guess, as to what the capabilities are within the nuclear metrology group here at NPL. Most of the sort of work that we've been doing has really been to try and help with the development of separation schemes for the preparation of really difficult to measure nuclei. In the past couple of EGMs, we've had the opportunity to present some of the updates and the progress that the group has made on that. The other area is to look at the use of tandem ICP-MS, where a lot of work has been done to look at measurement of some of these nuclei. And the last capability, which will be covered in this talk, is looking at the supply of traces of mass spec tracer materials, which are not of access or have limited availability. An example that I'll cover today is technetium-97, where we've sort of had some ongoing R&D work with a PhD student based at the University of Birmingham, looking at sort of cyclotron production of the technetium tracer materials. And really to be able to do this, we had to rely a lot on really optimizing separation methods that allow the bulk removal of the target and then preparation of the tracer. So I'll quickly cover a bit the challenges associated with that and the progress we've made there. So just a quick overview as to technetium. So this was covered quite really well earlier, but I'd just like to kind of talk about why mass spec is quite a preferred method for measuring technetium, and that's simply because of its very long half-life is well suited for it. And both for both technetium isotopes here, essentially what we really need are really effective pre-concentration methods that allow for pre-concentration of technetium. In the case of Tech-99, a lot of work has been done to try and look at alternative methods to the normally sort of fission-produced molybdenum-99 that is used for the preparation of these regenerators. But in both for both nuclides, essentially what you do really need is a way of ensuring removal of interferences before you do your measurement. So following on from this, what are the challenges associated with measuring technetium? So you're able to have two approaches for measuring technetium-99. So you can use liquid scintillation counting and also mass spec, most commonly tandem ICP-MS. However, for both measurement techniques, some removal of interferences is required. So in the case of SYNT, you need to have some way of removing the beta-emitting interferences that may be present in your sample. And then for mass spec, if you're looking to measure technetium-99 en masse, then you also have interferences that are in the way. So a list of sort of common interferences I've shown there. So ideally what you would need is a very nice separation method prior to measurement to remove, in this case, ruthenium and molybdenum to help with measurement. And even then, it's still very, very challenging, and it requires online chemical separation and other other features of the instrument itself to kind of really help you measure at the levels of sensitivity required. So I mentioned, or I alluded to earlier, the work that we've been doing to look at production of trace materials. Before I go into that, it would be quite useful. I think this is probably really clear to everybody, but kind of go over why traces are important. So with a lot of these complex sample matrices, you need some type of way to work out what the yield is of the processing you're applying to your sample. The technetium, there aren't any stable isotopes that can be that exist. So we're relying either on using chemical analogues or really short-lived technetium isotopes to help with measurement. So ideally, what we would like is to have a tracer that is identical to our analyte, so that we can track the process. And then for mass spec, what would also be ideal is to have a long-lived tracer. In this case, technetium-97 is well suited for that. But before I kind of go into detail about the work done there, I would like to kind of just use the next couple of slides as an opportunity to give an overview of the work done the past couple of years by the group to look at separation methods for technetium and looking at the new developed materials like Tristan have for that particular for post-separation. So typically, TIVO resin is used for technetium separation, as can be shown on the plot on the right. There, have very high optimal retention of technetium under dilute nitric and hydrochloric conditions. But the challenge here is the need for very high nitric molarities to collect your technetium, which is not ideal if you're looking to do direct liquid syn and mass spec measurement. So this is where the newer resins that Tristan have, so TK201, are very well suited to help overcome the challenge of having to elute your sample in high nitric. So this is shown here and was shown by the group in the user group meeting a couple of years ago, where we characterised some of the newer resins that Tristan have, so TK201, which is based on this tertiary amine extractant. And we were able to demonstrate that if you're looking for softer elution conditions, TK201 was a good candidate for this. So I think hopefully this is quite familiar to all of you, but I thought I'd use this as an opportunity to kind of just show from the developments made what the ideal separation scheme for separation would be. In this case here, we're looking at the characterization data for TK201. Very dilute nitric is ideal for tech retention. And if you're looking to remove interferences that affect mass spec measurement of technetium-99, then you're able to remove those with the use of really dilute nitric. And then you can use softer elution conditions in this case, 2 molar or less of nitric to allow you to elute your technetium. So you have a very nice, quick method to do your separation. And if you're looking to change the elution agent, you can also use ammonium hydroxide, where again you have maybe a better level of recovery, which is shown here. So I thought I'd just use this as an opportunity to kind of just show what an ideal scheme would be if you were looking to do Tech99 separation on an environmental sample. And in this case here, this is the final scheme in place. And if you look at the emission profile, you have very nice recoveries with up to about 10 mil of eluting agent being used. So that's just a quick overview of the sort of work done prior for TK201. And the next couple of slides, I'll look to sort of give a nice, hopefully a nice overview of how we've sort of done a bit more work since that UGM to look at approaches that can be used for Tech97 separation and preparation as a tracer. So, like I said, technetium 99 is increasingly being measured by ICP-MS, but there isn't a tracer that's well suited for mass spec that's currently available. If we look at what's been reported in the literature, the ones that have been reported are mainly really short-lived tech nuclides, and stable rhenium is the other that is typically used. There was one, or I think several papers in the late 90s that I've looked at production of technetium 97. And this would be really well suited for ICP-MS as it's a very long-lived nuclide, but it's not something that is commercially available or available at all by anyone that I know of, at least. So any sort of routes in production, or any sort of work looking into production of Tech97 would be something that would be of interest to the community, I think, or people who are interested in doing Tech99 measurement or looking for a suitable tracer. To produce this material, you have to look at some sort of irradiation route. And this was work done as part of a PhD the last couple of years, which is based at the University of Birmingham, where there's a cyclotron facility. And this student just quite like a lot of nice work looking at ideal irradiation conditions for the production of, in this case, the initial production of ruthenium-97, which decays down to Tech-97. And it looks at optimizing the production routes, and was able to demonstrate quite a nice approach of irradiating molybdenum, a natural molybdenum target, to initially produce ruthenium-97, and then making use of some very nice Tech-selective separation routes to allow for collection of the ruthenium-97, allow that then to decay down to Tech-97. So with this particular project, what you really need is a nice way of pre-concentrating your ruthenium-97, removing the bulk material, which is the molybdenum, and find a way to demonstrate that you collected an isotopically pure Tech sample. To do this, there is another TK resin that is very well suited for this, and was shown and was presented, I think, in the UGM two years ago by a group over in Palatin, who have looked at using TK202 for separation of molybdenum from technetium. And the extractant system on TK202 is very well suited if you have a sample that contains a high amount of molybdenum. And this works out in our favour, as the systems that we're looking at in the irradiation and the target that we're looking at is the majority of the composition is obviously molybdenum. So this particular resin is very, very nice and works out really well in the system that we're wanting to apply the separation to. But there are a couple of things that were unclear, or that we hadn't really tested, which was to see if we could have a high ruthenium uptake using this resin. So we looked to do some testing with TK202 to see if we're able to have have high retention of ruthenium, and we did some method development work prior to looking at irradiation of molybdenum to sort of have a nice method in place. So in terms of the requirements of the methods that we had in place, we're looking to have an approach which will allow for, which would be capable of handling very high levels of molybdenum, which was demonstrated by work done by Palatum. But the one thing we were unsure about was to see if we could collect a nice clean ruthenium fraction during the initial separation. So to address this, we did some initial method development with TK202, where we looked at preparing a aqueous stable mix with molybdenum, ruthenium, and rhenium as an analog for technetium, to see if we could firstly address the sort of challenge of having to handle large amounts of the targets, in this case natural molybdenum, but also to see if we could remove and know what the behaviour of the ruthenium was, and then rhenium, which was the analog we used to track the behaviour of technetium. So we did some initial method development and looked at loading our sample with under alkaline conditions, because to be able to dissolve the target, the most suited method is to do it with low volumes of low percentage volumes of hydrogen peroxide. And then we had to find a way to load that precipitate in low alkaline conditions, which is what was demonstrated to work well before. But with this particular work, what we wanted to do was to work out what the ruthenium was, or what the recovery was during the load step. But we're also interested to see if we can maybe optimize this approach a bit more. So we increased the range of alkaline conditions that we tested. So during this method development, we loaded a sample containing our molybdenum target that's been dissolved, a known amount of ruthenium and rhenium, and prepared that in a range of alkaline molarities, loaded the sample directly to TK202 resin, and then at the initial stage collected what we'd hoped was the majority of hopefully what would be ruthenium, and then we looked to elute the rhenium, or the analog here of technetium, using water. At each stage we collected fractions and we're looking to try and determine what the molybdenum breakthrough was both in our load and eluted fraction, but ultimately to know how much ruthenium was recovered during this load stage and how much rhenium, the analog of technetium, was in the eluate. So here are some of the data here that was collected. So you can see that generally during the load step, in the range of alkaline conditions that were tested, we had very high ruthenium collected, which was good. We were able to answer the question that we had as to where the ruthenium would end up. And hopefully you can see during the elution step, there was very low molybdenum breakthrough, and the rhenium was also recovered in a high, had a high percentage recovery, and from that, the optimal molarity that was used for the final procedure was 5 molar sodium hydroxide, and that was simply because the lowest molybdenum breakthrough was observed with that particular load condition. So it's just some results, I guess, of the validation that was done. So earlier last year, we were able to have some time at Birmingham to do and irradiation of the molybdenum target to try and see if we'd successfully produced ruthenium-97 at the site. And we applied the method developed to this target. And this was done in 2 stages. The aim of the first stage was to try and collect the ruthenium-97 that hopefully was produced from the molybdenum target. So once the molybdenum target was prepared and converted into its aqueous form, we're able to directly load the sample in 5 molar sodium hydroxide onto TK202. And the main aim at this first stage was to essentially just collect the ruthenium-97. So we kept the load sample and did a gamma spec measurement, and we were able to identify that we had in fact produced ruthenium-97. And the advantage of this approach really is the fact that we shouldn't, at this point, have any of the neighbouring tech isotopes that could affect our measurement here, because that should all have been bound onto the resin. The second stage was to wait for the decay of the ruthenium-97 that was collected in this load solution, and in the ultimate wash solutions that were also prepared just to collect some of the ruthenium that might still be bound. And ultimately, after waiting for its decay, we applied the second separation using TK202. But for this stage, what we're interested in doing was to collect the Tech-97 that hopefully should have decayed in, and to remove the molybdenum that still would be might be present in the sample. So the scheme applied here was essentially using the same resin, same load, wash, and elution stages, but the sample that was kept was the elute sample, because by that point you'd hope that the majority of the tech was collected at that stage. And we did mass spec measurement on that sample to try and see what the amount of molybdenum was in the sample and if we'd adequately removed it. And we were quite optimistic, and we tried to sort of initially see if maybe we did have some Tech-97. So the question mark is there because we weren't able to successfully detect Tech-97, but we think we have approaches in place for trying to address the challenges that, or the things that are getting in the way of us being able to measure the Tech-97 rather. So here are the results. So after the separation, we did a mass spec measurement of the element that was prepared at this stage. And hopefully I think this is very clear, but the issue is the fact that even with the high molybdenum decontamination that can be achieved with TK202, there's still a lot of molybdenum in the final sample. So this needs to essentially be separated again, or another approach to sort of look at maybe looking at bulk cation exchange resins to try and remove that before trying to do a measurement again. But another thing that we've recently seen is, and this ties in with work already done by the group to look at tandem mass spec measurement of technetium. So there's been more work done to look at the reduction of molybdenum by using reaction gases. So combining online separation with a tandem mass spec and hopefully a more optimized molybdenum removal procedure will hopefully help us reduce the very high counts that we're seeing here. And in any case, this is work in progress, so hopefully with more radiation experiments, we'll be better placed to kind of know how to address this. The challenge of measuring Tech-97 when you have a lot of molybdenum. So just to conclude on the work with TK202, the products of Triscam have really helped us to have in place a very nice and optimal separation methods for measurement of technetium 99 by ICP-MS. And hopefully with some of the ongoing work that we're doing to look at production of Tech 97, TK202 is a resin which has helped us sort of make progress in looking at preparation of Tech 97. Like I said, this tracer is not widely available, so any progress made here will kind of really help us sort of be in a position where in future this can be something that is made available. So this was work done last year, and it's something that is very much still ongoing. So hopefully, with more opportunities to optimize this separation method, we'll be able to make a bit more progress. But as a summary, I think TK202 resin is very well suited for both molybdenum and ruthenium separation, and allows for very high tech recoveries. And hopefully, with some more refinement on our side, we can have a very nice method in place. Another advantage of TK202 generally is the fact that, unlike TK201, you're able to load your sample in alkali conditions. So it's also something that can be used in environmental monitoring samples that are of interest if you're looking to use a method where you're interested in loading directly under alkali conditions. So that's also another advantage of the resin. So just to summarise today's talk, I've hopefully have sort of given an overview of the different applications for technetium measurement and all of the different Triscam products that are available for doing technetium separation, and how in the past couple of years we've been able to use these resins to allow for us to make progress in the production of tracers. Hopefully, I think we have the aim to try and sort of have a general overview paper of the approaches that can be used for tech separation. So hopefully that'll be something useful in future. But to end, I think I wanted to kind of use this as an opportunity to kind of plug a new capability that we have at NPL, where we're looking to transfer some of the existing methods that we've developed to a new automated system that we have set up in our group. Like was sort of said in the talk previously, there's an interest to couple automated methods to ICP-MS, so we're really quite excited to try and see how this instrument helps us in the work that we're doing. And all of the methods that I've kind of covered in today's talk are ones that are very well suited to do automated separation with. And we kind of have a general interest to try and see if we can look at additional applications where automated separation would be well suited for this. So looking at high volume separation where you can reduce operator time, hopefully, to try and have methods in place. But within nuclear medicine, where there's an interest to have really rapid sort of automated methods, some of this hopefully will help us make progress in the sort of methods that we've already developed in the past couple of years. So yeah, hopefully it'd be something that we make good progress on and we can present in subsequent UGMs. And yeah, it's quite an exciting capability hopefully for us to look into. So yeah, all of this work would not have been possible with the support of Triscam and have access to some of these really nice materials that they've been developing. And a lot of the sort of progress that we've made here have been really helpful with the series of student placements that we've had, and the work driving the production of tracers was really spearheaded by a PhD student over at Birmingham, who hopefully has kind of helped us get to a place where we can make a bit more progress in making sure that there are tracers available. And with that, I'd like to thank for your attention, and happy to take any questions you may have.
Thank you very much for that nice presentation. This is true, we've been working with NPL for many years on many different projects, always a pleasure.
Yeah.
And we are looking forward to playing secure system
very
analytics.
excited.
I think there's a couple of good opportunities, especially for high volume water samples. Are there any questions?
Just how far away do you think the technetium 97 tracer actually is? Are we talking 2 or 3 years or sooner than that?
Not sooner, I think. I think we're hoping this year to try and look more into optimizing the molybdenum removal, and at that point have a good idea as to how well we can do that, and then maybe in the next 2 years aim to do another irradiation and then see how much material is possible to produce. But at the moment it's still R&D, but with an aim to just try and work out what's feasible to produce.
I mean, something we're very keen to have. So.
Yeah, hopefully we make good progress.
Okay, Maximilian, you got a question?
Yeah, I do. Actually, thanks for that very nice presentation. I agree with you that it's like really sort of complementary when you look at the style or the type of work we are doing in Münster. I have a question regarding the loading conditions of the TK202 resin. Have you by any chance tried loading some sample within not sodium hydroxide but ammonium hydroxide solution, and have you seen any retention there? Or
That's a good question. We only tried with potassium hydroxide. We don't actually looked to see loading with ammonium hydroxide. Might be something that would be quite useful to have data on to see if there's any difference in retention. So maybe it's that one.
Also, it's a good question. We never tried it. The hydroxide is the main part. It needs to be iron hydroxide. So it's really quite possible that ammonium hydroxide might be an option. So yeah, that might be actually quite good for you. That's right.
Yeah. That was
not bad,
maybe the little back thought.
That's right. Think about that. That could be quite small, actually. Nice.
Yeah. Thanks again for the very nice presentation.
Thanks for that. That's quite good data to have.
So how much lower do you need to get with the monotone? Factor, the contractor, then
probably the same again. Probably so either looking at a combination of tandem and the cation exchange resin, which will very kindly sent us. So we should hopefully have an opportunity to kind of see how we can do that.
It should be quite good that the C8 and the aluminum side can 6 is not. That's a tough one. So,
yeah.
We'll see.
We'll see how well we can do.
Yeah.